So most of you are here. Let's start on the class. So I may as well get started. So we're probably going to finish chapter 24 today. The worksheets for chapter 21 through 24 are due on the 23rd. They're on Brightspace. That has a small. What the hell? All right. Homework consisting of problems from the book is also on Brightspace, and it's due on the 23rd. And the exam on chapter 1 and chapters 21 through 24 will be on the 23rd. So that's not next week, but it's the week after on Tuesday, because we're ahead of schedule. We're likely to finish chapter 24 today. I will adjust Brightspace to make the next set of stuff available when we start up the next set of slides that you can work ahead. But the test, I'm not moving, because that's when I put it on the schedule. There's no reason to move it up. So you'll just have a little longer to study for it. So the exam will be on the 23rd in class. I'm still working on putting it together, but it's looking like it'll be 60 multiple choice questions. But I put 60 to 70 just because I'm still working on putting it together. Yeah. That's what I wanted to cover. There'll be multiple choice. Probably be using a Scantron sheet, but I'll go into that in more detail next week. So we were talking about stars and their death. So when stars die, smaller stars blow off their outer layers and leave behind the compact core that collapses to form electra into the form of what's called electron degenerate matter, which is basically matter being held up by the fact that there's only so many, you can only put so many electrons in the same place. And more massive stars that are more than 8 times the solar mass, they terminate in supernova explosions. When these collapse, the core is strong enough that it's able to force the electrons into the nucleus of the atoms, converting the protons in the nucleus into neutrons, and you end up with a massive ball of neutrons. This process causes a sudden pause in the collapse of the star, which the collapsing outer layers bounce off of, and it releases an enormous quantity of neutrinos, which superheat the layers above. This causes a massive explosion. This is relatively rare because most, you have to be more than 8 solar masses. But at supernova, and these stars don't live as long, so they're not that common. Like there aren't any nearby stars in our galaxy that could go supernova for anytime soon, for example. They become millions of times brighter than the prenova, and they leave behind either neutron stars or black holes. So the smaller of these large stars leave behind neutron stars. If the core is bigger than about So if the eventual core ends up bigger than about 3 times the mass of the sun, it collapses into a black hole. Go ahead. Oh, apparently. Just a second. Let me check that I have the right slide. Yes. Thought I moved some stuff around. Sorry about that. I thought that was apparently when I was adjusting this, I didn't do it right. So all stars consume their nuclear foil. They collapse into either a white dwarf, a neutron star, or a black hole. That's what gets left behind. A white dwarf is small. Some are no larger than the Earth. Generally, white dwarfs are around the size of the Earth for a rough scale. They're dense. They can be more massive than the sun. They cap out at about 1.3 solar masses. And a spoonful of matter from them would weigh several tons. The atoms take up less space, and basically the only thing that's keeping them from collapsing anymore is the Pauli exclusion principle, which says basically electrons can't all be doing the same thing. So you have to fill up the energy levels. So electrons get displaced inwards, and this is called degenerate matter. And they have a hot surface that slowly will cool to become a black dwarf eventually. As far as we can tell, from our best understanding, there are no black dwarfs in the universe because the universe isn't old enough. Because by our calculations, the amount of time it would take for a white dwarf to cool down into a black dwarf is significantly longer than the age of the universe. White dwarfs don't just last forever. They can actually explode and be destroyed in what's called a type 1 supernova. If a white dwarf has enough extra matter added to it, it will collapse. And that will cause all of the atoms in it to fuse simultaneously, and it'll go off like a bomb. So this is a white dwarf compared to the size of the Earth. And they actually get smaller as they get more massive, which is one of these contradictory things that happens with degenerate matter. A neutron star will form from a more massive star. The star has more gravity. It squeezes itself smaller. This is a remnant of a supernova, and the gravitational force will collapse the atoms inside the neutron star. The electrons will combine with protons to produce neutrons, and the whole thing will be compressed to a very small size. You don't get the explosion you get with a white dwarf collapsing, because in a neutron star, this core is made of iron, and so you don't get any energy out of fusing iron. So you just get the whole thing turned into one giant nucleus, effectively. A pea-sized sample of a neutron star would weigh 100 million tons, because it has roughly the same density as an atomic nucleus. You could actually figure out reasonable numbers for real neutron stars by assuming they have the same density as a regular atomic nucleus. It has a strong magnetic field, and the first one was discovered in the 1970s. It was a pulsar. So it was a pulsing radio source. So what happens is, because of the strong magnetic field, various particles falling into the neutron star will get flung off along the direction the magnetic field points. And the magnetic field doesn't usually point in the same direction as the axis of rotation. So the magnetic field will effectively sweep across the sky, through space. And when it points at us, we see a pulse of radio waves. When it points away, we see nothing. And when it points back at us, we see a pulse of radio waves. But these spin very, very fast. So for example, the pulsar found in the Crab Nebula, which is a remnant of the supernova that occurred in AD 1054, rotates 30 times a second. So it pulses on and off. And the first time a pulsar was detected, people thought it might be artificial. It looked fake because it was so regular as a repeating pulse. So this is the Crab Nebula with the pulsar in the center. This nebula is the remnants of that supernova explosion. This is all the stuff that got thrown out. Now, if that star is even bigger, you'll get a black hole, which is more dense than a neutron star. The intense surface gravity will let no light escape. And as matter gets pulled into it, that matter becomes very hot and emits X-rays. And black holes are common objects. We've identified a number of them. One of the examples that always is brought up is Cygnus X1, which is emitting X-rays. And it orbits a massive supergiant companion, and gases are pulled from the companion to form an accretion disk that spirals around a void. So we see an X-ray source, and we also see that massive companion orbiting another object that we can't, that's not emitting any significant light. So this is an artist's view of a black hole consuming matter from a giant companion star, and it will also produce jets of material coming out the ends. So we're massive stars, when they burn out and die. Okay, so this is in the wrong place. They become millions of times brighter than prenova, and they become neutron stars that produce black holes. So let's talk about galaxies, and I'll fix the slides after lecture. A galaxy is a collection of interstellar matter, stars, and stellar remnants that are all gravitationally bound to each other. So a galaxy is a big group of stars and stuff that is all gravitationally bound to each other, and generally, moving around, orbiting a central object or a central point. Galileo discovered that the Milky Way galaxy was made of stars, because it's not like you can't see it by looking up at the sky. You see this pale stripe across the sky, but it's not clearly made of stars unless you look at it with a telescope. But the first time it took until the 1920s, early 20th century, for us to actually realize that there was more than just the Milky Way, that there were other galaxies out there, and that they were actually separate galaxies. And the centers of galaxies, as far as we can tell, all galaxies have a supermassive black hole in their center. For example, our galaxy has one that's about 4 million times the mass of the sun. It's called Sagittarius A star. And now all other galaxies also have a supermassive black hole in the center. So they're collections of stars and interstellar matter that are gravitationally bound. So here are some pictures of galaxies. This is an oblique view of a spiral galaxy. This is an edge-on view of a spiral galaxy. This is one of the outer structures called a globular cluster that are part of the halo of a galaxy, spiral galaxy like our own. So these are some images of other galaxies. It's hard to take an image of our own galaxy because we're in the middle of it. And so, but galaxies are collections of stars. There's lots of galaxies out there. There's a similar number of galaxies in the observable universe to the number of stars in our galaxy. So here's a short video about spiral galaxies like our own. So galaxies come in several types. There's spiral galaxies, which are disc-like and have spiral arms, like our own. There are elliptical galaxies, which are round and sort of round shaped. And then there are irregular galaxies, which are irregular.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should have a better sense of the different varieties of galaxy shapes. So this Smart Figure is associated with spiral galaxies, and this is an example of a spiral galaxy here. Spiral galaxies are typically fairly large, and they measure from one side to the other about 20,000 to 125,000 light years. So it would take, approximately 125,000 years for light to traverse from one side of a spiral galaxy to the other. Some spiral galaxies have this central bar-shaped region. These are called barred spiral galaxies. So this would be like the bar here, and then the spirals come off of that, circling around it. We don't really know what causes these bar structures, but probably our own galaxy, the Milky Way, has a bar-like structure in the middle. We can't actually see that very well because, unlike this galaxy, we're within the Milky Way, so it's very hard to determine its structure from the inside. Typically, spiral galaxies have a greater concentration of older stars near the center, which gives the central bulge kind of a different color, like this yellowish color that you see over here, than what you see on the fringes of the spiral galaxy. And then if you look at them from the side, you can see that that central bulge bulges out away from the rest of the plane of the spiral galaxy. It's worth noting here that not all galaxies are spirals. This little fellow right here is a globular cluster, and this globular cluster is like a very small galaxy. It has only about 10 million stars. This is a look at the Fornax galaxy cluster, one of the nearest galaxy groups to our own local group. Galaxies come in these clusters, so while each of the galaxies is made out of many, many stars, the clusters can be made out of many galaxies. Our local group consists of about 40 galaxies, of which 3 are big classic spiral galaxies, like this one here that you can see in the Fornax cluster. The rest of the galaxies in the Fornax cluster are elliptical galaxies. Elliptical galaxies have an elliptical shape, so they basically are shaped something like a football or something like that. Some of the biggest galaxies we know of, and also some of the smallest ones, are elliptical in shape. Still, other galaxies have an irregular shape to them, such as these two galaxies here. This is the collision of the antennae galaxies, and their form isn't as geometrically regular as the spiral or the elliptical galaxies. And one reason for that in this case is that these two are colliding, and so their intense gravitational force kind of distorts and tears at their neighbor. Okay, so which of the 3 galaxies is this? Elliptical, irregular, or spiral? Well, hopefully you said that this is spiral, and you also probably noted that this spiral galaxy has a central barred region, so this is a barred spiral galaxy. Good work. Hopefully you got that correct. Thanks a lot for your attention. This has been another Smart Figure.
So, spiral galaxies, like our own Milky Way or our neighbor Andromeda, have arms that spiral outward from the nucleus. They make up about 30% of all galaxies. And about a third of them have bars in the center. They have a large diameter. It could be up to 125,000 light years. They contain both young and old stars. And a barred spiral galaxy, the stars arranged in the shape of a bar in the center of the galaxy. They are generally quite large. The Milky Way is probably a barred spiral galaxy. And they make up about 10% of all galaxies, so about a third of spiral galaxies. And the other 2/3 are what are called normal spiral galaxies. The easiest to see nearby is the Andromeda galaxy. And I think to our modern understanding, the local group has gone off in number a little. It's more like 50 instead of 40 galaxies. There's a bunch of little ones, and there's 3 big ones. So this is a dramatic image of the spiral galaxy Messier 83. So this is a spiral galaxy. No, 83 was an elliptical galaxy. Oh no, that's 87. Sorry. A large number of the easier to see galaxies got recorded by Messier, and so are part of the Messier objects. So there's a whole collection of objects that are Messier numbered. Messier was looking for comets, so he made a list of all the things that looked vaguely like a comet but didn't move, so weren't comets. So basically all the like fuzzy blobs, and a lot of those are galaxies. So Messier 83 is a spiral galaxy. Messier 87 is a large elliptical galaxy. That black hole picture I showed you on Tuesday was from the image of a black hole that I showed you earlier. That was from Messier 87. That was the supermassive black hole at the center of that galaxy. Here's a barred spiral galaxy. You can see the distinctive bar that and the arms come off the ends of that. Elliptical galaxies are ellipsoidal in shape. That means they could be like, they're ball shaped. They cover most balls one might call a footballish shape, ranging from, more stretched out elliptical galaxies, which are more American football shaped, or rounder elliptical galaxies, which are more international football shaped. But they're ball blobs. They have lots of randomly orbiting stars that form a round shape. They make up about 60% of galaxies. They contain both the smallest and the biggest galaxies. Most of the, by count, are the dwarf galaxies, the smaller galaxies. So for example, there's like half a dozen to a dozen dwarf galaxies basically orbiting the Milky Way. Several of which are being consumed by the Milky Way. Galaxies do cannibalism. Galactic cannibalism is a thing. If you're a small galaxy and you get too close to a big galaxy, you get torn apart by the gravity and integrated into that larger galaxy. And we know this has happened because there's evidence of it in the Milky Way, and evidence of it actually actively happening with some of the small galaxies orbiting the Milky Way. So most of them are smaller than spiral galaxies, they're dwarf galaxies, but the largest known galaxies are also elliptical galaxies. And it's thought that possibly the very large elliptical galaxies form when 2 spiral galaxies collide. So it's not entirely known. So there's a large elliptical galaxy. M87 I mentioned before is a large elliptical galaxy. So you can see, big round blob. Spiral galaxies are much more interesting to look at. They have much more structure. And then irregular galaxies don't have symmetry. They're some funny other shape. They're distorted elliptical or spiral galaxies. They're about 10% of all galaxies. They contain mostly young stars, and this includes the Magellanic Clouds, which are the 2 galaxies closest to us. They're 2 of the galaxies that are basically orbiting. Oh no, they aren't the closest actually. but they're among the closest galaxies to the Milky Way. They're orbiting the Milky Way. I believe the galaxy that's actually closest to us wasn't discovered until quite late, because it happens to be on the opposite side of the Milky Way from us. So the center of the Milky Way is in the way. But they contain mostly young stars, and it includes the Magellanic Clouds, because they're sort of being torn apart by the gravity of the Milky Way. And galaxies come in clusters. You get groups of galaxies that are all gravitationally bound to each other. Some contain thousands of galaxies. Some, like our local group, contain 40 to 50. So our local group contains about 40 to 50 galaxies. And you can have clusters of clusters, which are superclusters. These are huge swarms of galaxies. And this is pretty much the largest structures we see in the universe. And we see clusters of galaxies sort of in like long chains. But here's the Fornax galaxy cluster, a number of elliptical galaxies, and here's a spiral galaxy. Our local group has 3 big galaxies in it: the Milky Way, the Andromeda Galaxy, and M33. And we didn't start to realize that galaxies were actually separate galaxies made of, millions and millions of stars, until Edwin Hubble started observing them in the 1920s or so. So it was originally proposed by Immanuel Kant in the mid-1700s that possibly these telescopically visible fuzzy patches of light were distant galaxies, and he described them as island universes, but it wasn't popular at the time, and it wasn't really picked up because no one had actually seen stars in them. And Edwin Hubble in about 1919 tried to solve the fuzzy patches problem with the world's largest and most advanced telescope at the time, and was able to figure out that the Andromeda Galaxy he was able to figure out how far away it was. And it was way further than anything else. And he made observations of stars in it and determined that distant objects were well outside the Milky Way. Well, they were outside the Milky Way. They're not hugely distant. Yeah. I mean, the Andromeda Galaxy is relatively close to us. It's actually on a collision course with the Milky Way, so it will eventually collide in about 4 billion years or something. And he was also able to start identifying the motions of these various galaxies and how they were moving and where they were and such. Hubble. And he had the most advanced telescope in the world at the time, which is why he was doing this. So the study of the universe is cosmology. So if we want to talk about the study of the origin of the universe, the possible future of the universe, just the structure of the universe as a whole, that would be the study of cosmology. And the field of cosmology really got the modern stuff started with general relativity from Einstein, but also the work of Edwin Hubble made some very important discoveries that led to the idea of the Big Bang theory. So Edwin Hubble, he identified that there were these other galaxies out there. And then he started to figure out how they were moving. And he discovered that all the galaxies were moving away from us. Not all of them, but most of the galaxies were moving away from us. And in fact, the further away galaxies were from us, the faster they were moving away from us. The only galaxies that were moving towards us were a handful that were very close to us, like Andromeda. They're all in our local group. But in general, galaxies are moving away from us, and the further away they are, the faster they're moving away from us. And this matched up with a possible solution to the equations of general relativity of an expanding universe. And actually, Einstein, because when Einstein put together general relativity, it was thought the universe was steady. It didn't change over, it was just going to be around forever and stay more or less the same. So he put it in an actual term to correct for the possibility of an expanding universe or a collapsing universe. But then Edwin Hubble discovered the expansion of the universe, and certain ideas that had been around about the universe having a beginning and starting at some point started to be put together. So the Big Bang theory is that if you have an expanding universe, that means the universe used to be small. So the Big Bang theory is very early, the universe was hot, dense thing. So about 13.8 billion years ago, all energy and matter in the universe existed in an extremely hot, extremely dense state, and started to expand. It's often, people talk about it like it's an explosion, but it's not really that, because it's not exploding into everything. But the universe is expanding, and it continues to expand, cool, and evolve. It's thought the first stars formed about somewhere between 200 and 500 million years after the Big Bang. We don't know exactly. That's a field of active study where we're trying to figure out when they formed. We keep finding that they seem to have formed earlier than we expected. It was first thought that maybe it was like 1 billion years, then like 500 million, a little closer to 200. And these were just composed of hydrogen and helium, and stars have recycled and produced heavier elements over time. So what we've been finding is we've been finding older and older stars that are clearly not the first generation of stars. So like they have the stuff that had to have been created in previously existing stars. So yeah, we're not really sure exactly when the first stars formed. People are trying to figure that out. But 200 million years is a reasonable number. Somewhere between that, maybe 200 million, 400 million, somewhere in that range. And we observed that most galaxies have a red spectral shift. Their wavelengths are shifted to be longer, which means they're moving away from us. And the further away they are, the bigger their spectral shift is. So this leads to Hubble's law, which is a description of the expansion of the universe, and it's that the recessional speed of galaxies is proportional to their distance, and this accounts for redshifts. It explains the cause of these redshifts. And this is also really helpful because this gives us another way we can measure distance. So this was put together by using various techniques to figure out the distance to various objects and comparing that to their redshifts. Generally, for distance stuff, we use type 1a supernovas, which are all identical. And so we know how bright they are. And so you can figure out how far they are from how bright we observe them. We know exactly how much light they put out because they're all identical objects exploding. And so then we can measure their redshift. But yeah, the recessional speed of galaxies is proportional to their distance. We can use this. This is the most common way that distances are measured for random objects. And this is because the universe is expanding. So a classic analogy is a raisin bread model where we have the galaxies throughout the raisin bread. The dough expands as the bread rises, and all those raisins spread apart. So everything is moving apart from everything else. So We see all galaxies moving away from us. Every other galaxy sees all galaxies moving away from us. What's going on is the space in between galaxies is expanding and getting bigger. So we see a redshift on all distant galaxies, demonstrating the expansion of the universe.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should have a better grasp of redshift and what it tells us about the nature of the universe. When we look at distant galaxies, we observe something rather interesting, and that is that they are redder than we would think that they ought to be. In other words, the standard spectral lines that emanate from any sort of light source in the universe are shifted in most cases towards a redder wavelength. So, for instance, this particular spectral wavelength here is shifted to this one. And so basically the whole package is shifted over to the right towards longer wavelengths. So red light has a long wavelength and blue light has a shorter wavelength. This is important because it basically reveals whether or not these light sources are getting closer to us or moving away from us. A common everyday example that you've probably experienced of this effect, sometimes called the Doppler effect, has to do with an ambulance moving towards you. In this case, we want to pay attention to the sound that that ambulance is giving off. So its siren is blaring, it's giving off sound, it's moving towards you in this upper image, and that means that the source of the sound is getting closer and closer, so the apparent wavelength of that sound basically gets compressed. On the other hand, once the ambulance passes you or moves away in the opposite direction, it's still producing that same sound, but now it's moving away from you, so the apparent wavelength gets stretched out. And so you would experience this as basically the ambulance sounds like it's a higher pitch when it's moving towards you, and the siren sounds like it's a lower pitch when it's moving away from you. So the lower pitch one is kind of like the red shift. All right, so obviously there are no ambulances in space, at least none that we know about. What we're looking at instead is this sort of stretching out of the light signal, just like the ambulance moving away from you is stretching out the sound signal. Now this is important because basically no matter where you look in the universe, everything is moving away from everything else. And a good analogy for this would be raisin bread. So here's a loaf of dough that's going to be baked and made into raisin bread. As that dough rises, the dough expands, and the individual raisins get further and further apart. No matter which raisin you're on, if you look at the other raisins, they all look like they're moving away from you because they are. And this is an analogy for the universe. No matter where we're located in the universe, everything else is moving away from us all the time. And so this implies this movement that things were closer together in the past. Cosmologists have been able to back calculate the moment in time when everything was completely packed into one very small point. And of course, that time is called the Big Bang. All right, so basically that's taking the expansion that we observe in the universe today and just basically back calculating to when everything was close together. This redshift, which might seem so minor, actually reveals this fundamental feature of the universe, that it's getting bigger and bigger over time. So this gives us a new perspective when we look out on distant galaxies like this one. There's two things that occur to me here as we look at a galaxy like this. One is that we're looking back in time. You know, it took time for this light to traverse the tremendous distance between these distant galaxies and Earth. In some cases, you're looking at light that left those galaxies billions of years ago. And so it's traveling across space for billions of years before finally entering your eyeball so you can register that this is a distant object. So it's really like looking back in time. And second, that every object that we're looking at, with a few exceptions, is moving away from us and getting further away with each second. So that's sort of a little bit sobering in terms of, science fiction and thinking about traveling to these distant star systems. It's getting harder and harder to do that all the time. What does this imply about the fate of the universe? Is the universe going to keep on expanding forever and ever, and ultimately all the galaxies will get really, 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 really far apart? That's a possibility, and that's called an open universe, basically expanding forever and ever. And if the universe isn't really all that dense, if it's below a critical density, then yeah, we'll probably get an open universe in the future. Another possibility is if the universe is above a critical density, then its expansion will slow and gravity will eventually pull it all back together into a single point again, and that single point is known as the Big Crunch. It's sort of the opposite of the Big Bang. Right now it looks like we don't have enough mass to do that, but dark matter may end up basically allowing us to get into the Big Crunch. We don't know which it's going to be, basically getting lonelier and lonelier in the future or getting crushed into smithereens. Either way, it sort of gives us perspective on our place in the universe. Thanks a lot for your attention. This has been another Smart Figure.
I believe currently to our best understanding, we're in an open universe, especially because this might be this, I don't know, it was a little bit. When we started to understand about dark energy, which is actually causing the universe to expand faster, which we really don't understand anything about. We just know it's happening. The universe is expanding and it's speeding up. And there's a possibility that that will mean at some point the universe will literally tear itself apart. We don't know. But some of the predictions of the Big Bang Theory, the universe was once unimaginably hot. And that means that researchers should be able to detect the remnants of that heat. There should be a point where the universe was so hot it was basically opaque and glowing, much like the surface of the sun. Turns out going back in time through the history of the universe is kind of like approaching a star. So there was a point where the universe was hot enough and dense enough to be opaque like the surface of the sun. So we should be able to detect that. Because the universe has expanded, that remnant of that glow from the early universe would be in the microwave spectrum. And in the 60s, I think it was the 60s, it was found by accident. A couple of researchers were setting up a microwave telescope in New Jersey. They were going through and eliminating all their sources of noise. And they had this one persistent signal that just would not go away. They looked for all the possible things it could be. They even checked if it was caused by pigeon poop. And it turned out it was real. It was coming from everywhere. And it was the echo of the Big Bang, and it matched up almost perfectly with what the theoretical models said it should be. Because a few years before, people had modeled what the signal from the Big Bang would look like. And it's a black body spectrum at a certain temperature that you can work out. And this background signal, the cosmic microwave background, is like a perfect match to it. And so the fate of the universe, there's a few possibilities. Two main ones. There's this sort of big chill. The universe will just expand indefinitely. Eventually, all the stars will burn out. Galaxies will become more slightly separated in an endless, cold, dark universe, which is not the most pleasant thing. The other major possibility is the big crunch, where the outward expansion will stop, gravitational pull will take over, everything will collapse back inwards, and we have a big crunch. To our current understanding, the big chill is the most likely option, but understanding how the expansion of the universe will act involves understanding how dark energy works, because we know the universe is, we've observed that the universe's expansion in more recent history of the universe has been speeding up, which is not what you would expect. You would expect it to slow down from the gravity, pulling everything back together. We just had some initial outward expansion and it would slow down, but it might be not expanding. You know, it might be expanding fast enough that it'll never come to a stop. But what we've observed is that actually, not only is it expanding, that expansion is speeding up. Because people were trying to figure out maybe it was whether it was going to go big chill or big crunch. And they were expecting, how fast is it slowing down? They were asking. And then they found it was speeding up. And they're like, what? And so people are working on trying to better understand this acceleration of expansion and what all is going on there. These measurements are very subtle and tricky. And what will continue to happen depends on our understanding of what that acceleration caused by dark energy is. And honestly, we don't have a good understanding of that. So, but yeah, so these are the two big possibilities. There's that third fun one where if that expansion, the speeding up of the expansion, if that gets going faster and faster, if it gets fast enough, it might be enough to start tearing matter apart. You get what's called the big rip. So there's sort of a cosmic tug of war where we have the current universe. One possibility is gravitational collapse caused by the dominance of dark matter pulling it together. Another is the big chill, infinite expansion resulting from the dominance of dark energy pushing the universe apart. To our best understanding, dark energy is currently winning, but we don't know how dark energy works, so we don't have the best understanding. So there are two types of dark stuff that actually make up most of the universe. These are dark matter and dark energy. Dark matter is something we detected when we started to look at galaxies, and we noticed that they were spinning too fast for the amount of stuff we were seeing. Because galaxies are gravitationally bound. To keep spinning around at a certain speed, there needs to be enough matter to pull inwards strong enough to keep things in those orbits. And when we calculated the amount of matter and compared it to the amount of matter we saw, we were missing about 80% of the matter that should be there. So gravity states that all stars closest to the galactic center should travel faster than those further away. What we actually see is that they're traveling similar in speed, which implies the existence of a whole bunch of extra matter. So dark matter holds together our galaxy and galaxy clusters. We've also observed it via what's called gravitational lensing. We've observed dark matter in between galaxies, bending light from distant galaxies, things like that. So we know dark matter exists. We have some ideas about what kind of thing it must be, because we can model our current universe and what properties dark matter had to have had to form our current universe. So basically, we can say it's not stuff like black holes or big dark objects, because we notice them via things like gravitational lensing, and we don't. It's not something really tiny and fast moving like neutrinos, which were a considered possible source of dark matter, because it turns out they would be moving too fast, and you wouldn't get the kind of structure we see in the universe. So it has to be something that's called cold dark matter, which is thought to be heavy exotic particles that we have yet to identify or maybe create in particle accelerators. So we think they're all over the place, but in all likelihood, they barely interact with anything and only primarily interact only gravitationally. So there's a lot of guesswork in trying to find actual dark matter. But we know it's out there. We know it holds our galaxy and other galaxies together. And dark energy, well, as the universe expands, gravity should be slowing down that expansion. You know, everything's going outwards, but everything is pulling on everything else, so it should slow down. But it doesn't. It's speeding up. So something is exerting a force that pushes empty space apart, or the matter apart, or the empty space between matter apart, causing the expansion of the universe to accelerate. We know there's something. We can make an estimation of how much energy it has in total based on the rate of acceleration. That's about all we know. Very little is known about dark energy. We have some idea that it kicked in later in the history of the universe. That it wasn't particularly, it started to kick in as the universe got bigger, but again, not much is known about dark energy. So that is the end of chapter 24. Any questions? Anything you'd like me to go over? I'm happy to rant about astronomy stuff because I'm also teaching an astronomy course. but if you want a much more detailed and possibly philosophic view of the history of the universe, I can suggest the podcast The Universe from Crash Course, which goes over the history of the universe and its future. Yeah.
Is it on YouTube?
Yeah, it's on YouTube and like all the podcast places.
Check it out.
Yeah. And it's complete, so. Yeah, so that is the end of chapter 24. So we'll be having the exam on the 23rd. That's not next week, but the week after on Tuesday. It'll be about 60 to 70 multiple choice questions. I'm planning 60, but I gotta see what works out as I put it together. I'm not finished putting it together. It'll be mostly on chapters 21 through 24. I need to get back to working on it. Yeah, anything else? And the worksheets due on the 23rd, and homework number 1, consisting of problems from the book, is also due on the 23rd. And when we finish here, I will make the stuff for the next section of assignments, worksheets and stuff available. Because it's currently not set to be available until a bit later because we're ahead of schedule. Any questions about anything else? Well, since we're running ahead and we got through the whole section, I think I'll stop here for today. Have a nice weekend.